что можно начинать. Okay, good evening. Our today's speaker is Boris Doubrov from Minsk. ODEs on the contact point and fiber preserving transformations. Boris, you're welcome. Please begin.
Yeah, thank you very much. It's always a pleasure to give a talk at this seminar. And today I will speak about a problem that, I was dealing with a long time ago, and I thought it was mostly done until the very recent year when we found out that this theory, equivalence theory of ODEs, can be extended to other pseudogroups of transformations. And that's what I will be speaking about today. And I should say this is a joint work with Professors Morimoto from Japan and Zelenko from Texas A&M. And that's still a preliminary report, so it's work in progress. I will present the results we have up to now, but I hope you'll see some gaps still. Just a second. So that's why did I get? Yeah, that's okay. So what do we study? So let's start with the setup. We just study scalar ODE, so arbitrary order k, and for us, k equal to 1 is somewhat trivial, so we always would assume that k is at least 2 or maybe higher. We'll be looking at these ODEs under the following transformations. So one of the most natural, to me at least, transformations would be contact ones, because this is a class of transformations that preserves order of ODEs. So it maps ODEs of order k again to ODEs of order k. And we all know what are contact transformations, I believe. So transformations on first jets, which preserves a contact form. And then you, of course, can prolong them to jets of any order k. This is exactly the case that was treated by me about 20 years ago. But there are also some other pseudogroups here that are of interest. Probably the most standard pseudogroup of transformations from the classical point of view would be point transformations, what we call. These are just transformations of dependent and independent variables, which we also lift to arbitrary jet spaces. And this is what we deal with essentially in our university courses of ODEs when we do substitutions and try to bring ODEs to some simpler form. And another class of transformations that are also quite often treated in this class, in this family of problems, is what's called fiber preserving transformations. So these are transformations that preserve independent variable, but do not necessarily preserve dependent variable y. So these are three classes of transformations, and they were pseudogroups, and I always think about them in local terms. So they're local diffeomorphisms, but I don't assume any global properties here. I always view the equation as just the case order ODE as just a codimension one submanifold in case jet space of maps from R to R. And of course, all these pseudogroups, as I mentioned, naturally belong to this jet space and transform the submanifolds. So act on equations. So in a way, in this setup, we would like to consider geometry of hypersurfaces in case jet space under the actions of infinite dimensional Lie transformation groups. it's as we'll see, there are some similarities here with more classical problems like hypersurfaces under affine projective transformations, or even Euclidean ones. But of course, here there are more things this is more challenging problem, of course. So what questions we are interested in? And a very basic question is when two equations are locally equivalent. So when we can, given two ODEs, when we can bring one to another via transformation for a given class. And one of the most important questions is when one of these equations is trivial. So by trivial equation, I always mean the equation case derivative of y is equal to 0. So the question is, suppose we are given an equation, can we bring it to a trivial one via transformation from a given pseudogroup? Such equations will be called trivializable under the pseudogroup. Well, G, I will use G, capital G to denote the pseudogroup normally. So in a way, we would like to characterize or explicitly describe, as explicitly as possible, describe the orbit of a trivial ODE under the action of the pseudogroup. And a few disclaimers. So what we are not going to discuss, there is a so-called problem of constructive equivalence. So suppose we manage to find out that two equations are equivalent, or one equation is trivializable, that's equivalent to the trivial one. This does not necessarily mean that we were able to find the transformation. That's an interesting thing, that to find the transformation, even if we know that the equation is trivializable, is by itself a separate task. So today we are not going to solve for these. We're just trying to find out when they're equivalent. It's not that this problem is totally unknown. There are approaches how to deal with such problems, but that's out of scope for today's talk. And another thing that I would be happy to touch maybe, but I probably won't be able to do this due to lack of time, that's how this generalizes to the case of systems of ODEs. And for systems of ODEs, because there we have to deal with maps from R to Rm, where m is greater or equal to 2. Well, we no longer have a contact transformation there. Well, we do have, but due to Lie-Blackwell theorem, they reduce to point transformations immediately. So we may still discuss equivalence of systems of ODEs under point and fiber preserving transformations. That can be potentially done, but that will not be present in the talk today. Well, and another main definition I would like to give, because I will all the time speak about invariants. So I'd like to clarify what kind of invariants I'll be dealing with. So they will always be, well, differential invariants and relative invariants, but they will be invariants of ODEs, which means this will be some expressions that involve the right-hand side of the function that defines an ODE. Or in more abstract terms, we may think about an ODE as I mentioned, this is just a hypersurface in case jet. So hypersurfaces, so GDEq has dimension k plus 2, so hypersurfaces of dimension k plus 1. So we may consider jets of such hypersurfaces of arbitrary order, and then, well, an invariant is a function. And because I speak about the relative invariant, it is not preserved. It's preserved only up to a multiplier under the action of a pseudogroup. We'll see examples of such invariants very soon. I'll show them in a minute. But this is a kind of invariance we'll be using to characterize, in particular, the classes of trivializable equations. And because we speak about relative invariance, only the condition that this invariant equal to 0 is preserved under the pseudo group. So each such invariant, each such condition defines a certain family of scalar ODEs which are preserved under the action of the corresponding pseudo group. And sometimes I will speak about fundamental invariants. And this is my goal, actually, to find this fundamental invariance. So we say that a certain family of invariants, such relative differential invariants, is a fundamental family, or a family of fundamental invariants, if actually they distinguish the class of trivializable ODEs. So in this talk, I will just say that certain family of invariants is fundamental, is a set of fundamental invariants if the conditions I1, I2, etc. are equal to 0 define exactly the class of trivializable ODEs, or define the orbit of trivial ODE under the group, pseudo group G. And the examples are very classical, very well known for lower order ODEs. Probably the most classical goes to the works of Tress, end of 19th century. So if you look at the second order ODE after point transformations, then it has the following two fundamental invariants. Well, notation is, I use the following notation. So numeric index means the derivative of function with respect to, well, jet coordinates that correspond to derivative of y. So like f1 is just the derivative of f, partial derivative of f with respect to y prime. So f1 means we take 4 derivatives of f with respect to y prime. 0 means we take a derivative of f with respect to y. And here in this case, we have y prime. And we also have x, but x here is something different. So x means a total derivative with respect to x. So when I have x here, which means that's partial derivative of x plus y prime partial derivative by y plus f times partial derivative by y prime. So it's total derivative on the equation. I should have probably written down this here, but that's just very standard notation in this area. So, and you see that first invariant in particular means so that the class of equations which are cubic with respect to y prime is invariant under point transformations. So if the right-hand side is just a cubic polynomial with respect to y primes, and any change of variables transforms it back to the same form. The second invariant is certainly way more complicated. If I were to express this in terms of just partial derivatives, so expand all total derivatives here, that would be like 30 or 40 terms here. It becomes really huge. And I'm not going to explain where it comes from now, but there is a nice geometric theory behind why exactly these two invariants are fundamental invariants. And in particular, the equation is trivializable, so equivalent to y2 prime is equal to 0, if and only if these two invariants vanish. And here we see that it's very constructive. It's very computationally effective to understand when an equation is equivalent to trivial or not. You just have to substitute the right-hand side into this formula and evaluate them and see whether they're 0 or not. But if they're 0, this doesn't immediately give you the transformation. So that's what I mentioned about the problem of constructive equivalence. So the history is that the first person probably who wrote down carefully these two fundamental invariants was Tress in 1896, and Elie Cartan in 1924 did this via the approach I will be using today, which is very geometric. It was based on projective connections. And somewhat similar, so this is an example where we look at second order ODEs under point transformations. So we can look at the example where we deal with contact transformations, and here comes third order ODEs, where the story is somewhat similar. So we again have two fundamental invariants. And the first one looks very similar. So it's again forced derivative of the right-hand side with respect to y2 primes in this case. And the second also has, well, some similarity. But I should note that these indices here I put under the invariance, so I4 and W3, also important. So 4 means we take forced derivative with respect to y2 primes, and 3 means we take 3 derivatives, but sometimes you see that we take one derivative or maybe 2 derivatives. And this is because we actually live in we assign different degrees to different derivatives. So in this theory, we assign degree 1 to derivative with respect to y to 2 primes and to total derivative with respect to x. So for example, this term f to xx is indeed of degree 3. But for example, derivative with respect to y prime has degree 2, and derivative with respect to y has degree 3. For example, this term f0 is of degree 3, and or order 3 if you like. And if you take this weight, so degrees into account, then these expressions become really homogeneous of the right degree. But that's again technical detail. Again, these two fundamental variants were well, actually, the big one is due to Wunschmann, as always. It's commonly known as Wunschmann invariant of third order ODEs. But in general, the fact that these are two fundamental invariants is due to Chern in 1939, and again he used a Cartan's equivalence method or Cartan connection approach. So what we would like to do, we'd like to generalize these examples to any ODEs of arbitrary order and to all three pseudo groups, so contact, point, and fiber preserving. Well, any questions so far? Because I will be now going into some more technical details. Okay, so how do we deal with such problems? So first of all, the approach is based on differential geometry. And in the end, we will also need the techniques of Lie algebraic homology. And honestly, I don't know any easier way to go through to these results. So elementary computations, when you just try to transform equations and see what's preserved, what's not, are certainly possible in some low orders, but this becomes extremely messy as soon as the order of equation goes up and the order of invariant goes up. So what is the setup of geometric approach? So viewing equation as an object of differential geometry. So first of all, I mentioned already that equations, scalar ODEs for me are just hypersurfaces in case jet. I will often use coordinate notation, jet coordinates, which would be x, y, y0, y1, etc., yk. And then our ODE turns into just a single functional equation that defines a hypersurface. But because I always treat equations which are resolved with respect to the higher derivative, yk, this means that essentially this equation is projected diffeomorphically onto the previous jet. Therefore, it carries all intrinsic structures from this jet space. Well, it's all. So what structures do we have here? So first of all, we have a contact distribution on in K minus first jet space. In jet coordinates, again, here is an explicit formula. That's it's two-dimensional case of scalar ODEs, very simple. And then we have, of course, tangent direction to the solutions. And that's defined by, well, this is exactly the expression for the total derivative I mentioned before. So I write it in terms of vector field. And this is a one-dimensional subspace into a contact distribution. It's, again, trivial to see that all these forms are vanishing on E. And in addition to this, we also have, so if K is at least 3, then we have then all contact transformations, but also point and fiber preserving transformations will preserve so-called vertical direction. So vertical direction is a direction which is tangent to fibers of the projection to previous jet space, so jet space of order K minus 2. And that's due to Lee-Buckland's theorem that if K is at least 3, then any transformations that preserves C will preserve actually this vertical direction here as well. So we have explicitly this direction is given by this vector field, so vertical vector field. And what's important is that this two vector fields, total derivative, and this vertical vector field define as a decomposition of C into the direct product of two one-dimensional subspaces. So we have contact distribution decomposed as E plus V. And this is exactly an intrinsic structure that can be studied by means of differential geometry. And in particular, we can also check, that's an easy computation, that this intrinsic structure uniquely defines ODEs of order at least 3 up to pseudo group of contact transformations. When I say uniquely defined, means that if I have two ODEs of order K, and if they have these decompositions locally equivalent, then intrinsically locally equivalent. So if you're able to find a local diffeomorphism between two equations that maps one decomposition to another decomposition, then actually it can be extended to a contact transformation that induces this transformation. So essentially, contact geometry of ODEs is just geometry of such decompositions of contact distribution into two one-dimensional subspaces. Moreover, actually only E has to be chosen, and V is uniquely defined by C itself. So moreover, actually we have many more distributions that are invariant. Again, due to Lee-Buckland's theorem, all projections to jets down to first jet are also invariant under contact transformations, and they can be uniquely recovered from the contact distribution itself, but not to zero order. You know that. And so in case of point transformations, our intrinsic geometry is different from the intrinsic geometry of intrinsic geometry under contact transformations, because we need to define explicitly this projection. So this completely integrable distribution tangent to this projection becomes a part of our intrinsic structure. And similarly, for fiber preserving transformations, we need to take into account the distributions that are tangent to the projection to X, to independent variables X. But anyway, in all cases, we can define some intrinsic objects on our equation viewed as a surface, hypersurface, and then reduce the question of equivalence under a certain pseudo group to the equivalence of this intrinsic structure. Yeah, so that's exactly what is written here. So two ODEs are locally equivalent under a certain pseudogroup G if and only if their corresponding intrinsic geometries are locally equivalent. And again, when I say intrinsic geometries are locally equivalent, that's exactly meaning that we can have an abstract diffeomorphism or local diffeomorphism between two manifolds, two equations viewed as abstract manifolds, which maps one intrinsic geometry to another. And that is maps one family of vector distributions to another family of vector distributions. So in our cases, all our intrinsic geometries are defined just in terms of certain actually completely integrable vector distributions, which sometimes sum up into non-integrable distributions. But if we have E and V, we can treat C as a secondary object. Well, now comes now we need to do now Lie algebra. We need a little bit of a Lie algebra here, and we need to define what's called the symbol Lie algebra in differential geometry. And normally is the quality still fine? Because I heard someone. Do you hear me? Hello? Am I here?
Yes, we hear you.
Okay, fine.
Yes,
Because
but not permanently.
There were issues with the
You are
connection.
disappearing. I mean, the voice, and then at
But
least
is it fine now?
yes, it's okay now. Yes,
Oh, okay.
thank
Well,
you.
thank you. What we'll assume is that for now we'll assume that we have equations of sufficiently high order, and we need at least order 2 for fiber preserving transformations, at least 3 for point transformations, and I already treated k equal to 2 before, and k equal at least 4 for contact transformations, and again k is a case of k equal to 3 I mentioned already before, and all other cases are really trivial. For example, all first order ODEs are equivalent under point and contact transformations, and all second order ODEs are also equivalent under contact transformations. So all cases where k is smaller are either known or trivial. So we can really concentrate in this higher order ODEs. And in all these cases, we can, the symmetry algebra of the trivial equation is well known. And it is for a fixed k, it's the same for all three pseudogroups, actually. That's an interesting phenomenon that even if we allow more transformations, going from fiber preserving to point and then to contact, the symmetry algebra of the trivial equation stays the same. And it is a semi-direct product of GL2 and an irreducible representation of dimension k. And well, very explicitly that's here. And again, I write it here projected to R2, but we can always think about this Lie algebra lifted to the corresponding jet space. It's composed, I wrote it here as exactly GL2. So GL2 corresponds to the first 4 vector fields here, dx, x, dx, y, dy, and then x squared dx plus k minus 1 x, y, dy. So, well, one can check that this is a 4-dimensional Lie algebra that's isomorphic to GL2. And then this is an abelian piece that corresponds to shifts along the solutions. That's exactly k-dimensional abelian piece in this Lie algebra, and this GL2 acts irreducible in this k-dimensional piece. And I mentioned this in detail because this will play an important role in the future. So the structure of this Lie algebra is actually one of the key ingredients in the technical calculations. Well, I will sometimes use G0. I will need it. So G0, so if I take this Lie algebra and prolong it to KSJ, it will act transitively on the trivial equation. So so our equation is of dimension k+1. This Lie algebra is of dimension k+4. So it will act transitively with a three-dimensional stabilizer, and this stabilizer is just a subalgebra in GL2. So, well, we can identify it with for example, upper or lower triangular matrices in GL2, if needed. And again, that is also kind of important. So the key technical, well, the key idea was that goes back actually to Elie Cartan. And then we need further works of, well, Japanese mathematician Tanaka and then Morimoto that explained how this can be generalized to other cases. So the theorem says that if you have an ODE and a pseudo group, so we fixed an ODE and a pseudo group G, then we can construct a natural Cartan connection associated to this pair. So I'm not going into detail what Cartan connection is and how technically it works. Briefly, Cartan connection is defined as a certain G-valued one form, connection form, on a certain bundle over our equation E. So actually our equation E, I mentioned that's k+1 dimensional. So we need to have a bundle which is k+4 dimensional. So the fibers will be three-dimensional. And then on this k+4 dimensional bundle, we'll have an absolute parallelism. So one form that at each point is one form with values in G, in the symmetry algebra of the flat equation. And at each point, this is an isomorphism. For those who see these Cartan connections or who feel uncomfortable what Cartan connections are, and you can always think about, like, for example, conformal connections. So conformal connections are associated to matrix viewed up to a scale, conformal matrix, or even in a simpler situation, we can think about a Levi-Civita connection. That's just a connection associated to a Riemannian metric, or pseudo-Riemannian metric. They are all particular cases of Cartan connections. So Cartan connection is something more general. Well, conformal connections actually are just Cartan connections, exactly. So the main idea is that we have an intrinsic geometry defined on our equation viewed as a manifold. And this intrinsic geometry is defined, of course, by the equation itself, but also by a pseudo group. We'd like to have a natural connection, a Cartan connection associated with this intrinsic geometry. And in particular, well, natural means that whenever we have an equivalence between equations, then these connections will also be equivalent. And why do we need connections? Because we know that connections allow us to answer many, well, construct invariants, like Riemannian curvature, Ricci curvature, scalar curvature, etc., or even determine when our object is equivalent to the trivial one. For example, if a metric is Euclidean, if it only leaves the curvature of Levi-Civita connection vanishes identically. So this is exactly the same kind of results we'd like to get, though we would be dealing with a bit more complicated objects in this case, and our Lie algebra is a bit strange, so it's a semi-direct product of GL2 and an irreducible representation. So I should mention that there are two words here. So we want to have natural Cartan connections. I already mentioned what natural is, but I didn't say how do we ensure that we have a natural connection. But we also have associated. And this kind of association depends on a pseudo group. And different pseudogroups define different, well, because, well, I mentioned already, different pseudogroups define different intrinsic geometries. As an example, I give a very technical example here. So let's see what does it mean that a connection omega is associated with a fiber-preserving geometry for these. And to define this association, we need to do it as follows. So we take any section of this bundle and take a pullback of one form to our equation. And on equation we have, I call it, we have line that is tangent to our solutions. We want the pullback of omega map this line into something that sits inside GL2, not in all G, but specifically into GL2 part of G. And in addition, we have a tangent direction to the projection to X, to the independent variables. And we need omega on this tangent direction take values in the abelian part of our Lie algebra G plus its stabilizer. So this is the precise definition of what association means for fiber-preserving geometry. And the similar definitions can be done for point and contact geometries. Well, technically they're just more formally here. Essentially, we'd like to align distributions we have on equation with certain subspaces we have in the symmetry in our symbol Lie algebra. So we want this Cartan connection to reflect the structure, intrinsic structure we have on the equation. But we have many associated connections. That's a very flexible condition. Again, if we look for a parallel with Levi-Civita connections, for example, we know that among, or we have a notion of a metric associated. There are many Riemannian metrics associated to a certain. There are many connections that preserve a fixed Riemannian metric, but only one of them is called Levi-Civita because it has no torsion, and all others will have torsion. So somewhat similar happens here. We have many associated connections, but there is one that is better than all others. We call it natural. And to define what natural connection means, we need to deal with the curvature. So we need to impose certain conditions to the curvature of this connection. And again, these conditions are somewhat similar to construction of a Levi-Civita connection, where we say that we'd like our connection to have no torsion. So how do we define such conditions in this case? And this is the story that, again, is known. I didn't need to invent it from scratch. So it is a logic that goes back to Cartan and then turned into formal notions of parabolic geometries, like conformal. That's the idea that I used in projective and conformal geometries, for example, back to Cartan. And the idea is that we need now to look at the Lie algebra G, and in particular at two things. We need to introduce a grading of G. So we need G to be a graded Lie algebra, and that's easy. In this case, we just say that our X will have degree 1 and Y will have degree K. And then actually d by dx has degree -1, d by dy has degree -k, and then all basis elements in G I showed before would be assigned certain degree. For example, G -1 is this one. So it's just a two-dimensional subspace. And if I start taking brackets, it will generate all abelian part of my G. So if I take brackets, if I differentiate x to the power k minus 1 dy, if I differentiate it by dx, it gives me all k-dimensional subspace that is abelian part of G. And actually, we need this. It will be all negative part of G, which is denoted by G minus. So this negative part of G is in nilpotently algebra. It's spanned by dx and then dy, x dy, etc., x to the power k minus 1 dy. So it's a k plus 1 dimensional nilpotently algebra. And it's generated by elements of degree minus 1. So the key algebraic ingredient we'll need is actually this Lie algebra cohomology complex. And again, I'm not going to define what this complex is and how to deal with Lie algebra cohomology. It's just a Lie algebra, not the simplest one, but still it's nothing really very fancy. So it's just certain vector spaces, and because it's a complex, it's differential operator between the spaces. But in this case, we need exactly this Lie algebra cochain complex and differential, of course, in this complex. So how do we use it to impose certain conditions on the curvature? So first of all, it can be shown that the curvature, this is a curvature, d omega plus 1/2 omega omega. It can be naturally viewed as an element that takes values in two cochains of G minus with values in G. And we'd like to impose, we'd like this curvature to take values in a certain subspace here, as defined by linear relations. So how do we define these linear relations? That's sometimes called a harmonic theory on this Lie algebras. So some Lie algebras have a good scalar product. I'm not going to define that's some similarity with Killing form and semi-simple Lie algebras. We don't have a Killing form here because, well, we do have a Killing form, but that's degenerate because our Lie algebra G is not semi-simple, but we can still find a good scalar product. And I'm not going to define what is good. Some invariance properties have to be called, have to hold. And what this good scalar product helps us, it can be extended to the elements on our complex, and then, as in case of Hodge theory, we just define a codifferential. And the regular differential increases it increases the degree of cochains, so the codifferential decreases the degree of cochains. And this is exactly the condition. So d star kappa is equal to 0 is exactly the condition we need. And again, this condition is something that was invented by Elie Cartan in cases of conformal and projective geometry, and then was generalized to semi-simple Lie algebras G by Japanese mathematician Tanaka, and I was just using the same technique for non-semi-simple algebra. So this is a very short condition, but of course, if you expand it with all the definitions, it gives you a sequence, it gives you a lot of linear relations on your curvature. And it can be shown that this linear relations guarantee that this curvature that there is exactly one Cartan connection among all associated connections that has this that satisfies this property. But this is particularity of contact geometry. What is also important that if you have a normal Cartan connection, then we can actually find out how many fundamental invariants in which degrees there are. they just correspond to second cohomology space. So far as this were just cochains, we have to switch to cohomology. And this plus, lower index plus, means that we are only interested in cohomology that sits in positive degree. We have gradings of G, so everything is graded here. So we are only interested in positive degree here. So in a way, finding out how many fundamental invariants are and in which degrees they sit can be reduced to a purely algebraic or linear algebra problem. Just need to compute a certain cohomology for some fixed Lie algebras. And that can be technically done. There are a few tricks here that not all elements here lead to non-trivial invariants. Some of them correspond to expressions that vanish identically. So needs to some extra work to identify which of them are really non-trivial. But again, these are all algebraic details that can be handled, and that was done by me, I think, in 2001. So now what is new? Now we would like to generalize this to the cases of pseudo-product and fiber-preserving transformations. So this is something that was not known so far. And it turns out that actually the same idea and more or less the same constructions hold if we just replace cohomology complex with another smaller subcomplex. And for example, in case of fiber transformations, this subcomplex is defined like that. So we need to consider only cochains that if we apply it to elements from this R-tuples from our abelian ideal, they end up again in the abelian ideal. So this is a restriction, and it can be shown that this restriction is preserved by the differential of the Lie algebra cohomology complex. So this is a real subcomplex. And it turns out that our curvature function for the connection associated with the fiber-preserving geometry of scalar ODEs sits exactly in this subcomplex, and the rest holds. So one induces scalar product in this subcomplex, one defines a codifferential operator, and so essentially the only thing that happens one replaces cohomology complex with a different subcomplex of this cohomology complex. And the rest of the construction works unmodified, and in particular, this gives us a proof that there exist natural Cartan connections associated with intrinsic geometries of ODEs viewed under contact point fiber-preserving transformations. And for more fundamental invariants are still correspond to the second cohomology of the corresponding subcomplexes. So the complexes change, the degrees of invariance change. They start to sit in different degrees, but the same ideas and the same techniques simply work as in contact case. So the rest is computation. And this is a part that is not completely finished yet, but we have generated enough results so that I can show you some interesting things here. So in order to, so most importantly, I would like to give you a very explicit characterization of trivializable ODEs under contact transformations that can be done in full generality. And for point and fiber-preserving transformations, that's done for ODEs of orders up to 6, including 6 so far. And again, that's just purely due to computational difficulties. So to give you explicit expressions for this fundamental invariance, I need to introduce some notation, some examples. And one particular class of fundamental invariance is known as generalized Wilczynski invariance. And they in fact come from the idea that if you linearize ODEs, then you may the linearizations naturally behave under contact transformations. So in short, if you look at just a scalar linear ODE, that's case order scalar ODE, and we look at a smaller transformation pseudogroup of transformations. So it's X independent variables that is preserved, but also Y is just multiplied by a function of mu, of X, sorry. And actually, this is the most general class of transformations that preserves linear equations. Then we can consider absolutely the same problem, like equivalence and trivializability, and that was done actually by Polish-American mathematician Wilczynski back in 1905, 1906. So it's again the very classical result I'm showing there. So first of all, using these functions lambda and mu, we have two functions. We can kill two coefficients, two leading coefficients in our linear equations, so pk minus 1 and pk minus 2. That's called canonical Laguerre-Forsyth form of the equations. And then it turns out that we can cook up some expressions from the rest of the coefficients. It's just these terms, these are factorials. They are a little bit similar to Clebsch-Gordon coefficients. They come from certain SL2 representations here. But the rest is just derivatives of the remaining coefficients with respect to X. So if you do this carefully, and that's what Wilczynski did, you find out that these expressions are actually exactly relative invariants of this class of equations, and moreover, they form a fundamental system of invariants, which means that our equation is trivializable. It can be brought to a trivial one if and only if all these expressions vanish identically. This was known for. Yep.
I'm sorry. What does superscript of at p mean in the
J minus 1?
Yeah.
That's just derivative with respect to X.
Okay, thanks.
So these are p with this complicated index is just one of the remaining coefficients after we got pk minus 1 and pk minus 2 equal to 0. And upper index is just the number of derivatives with respect to X. So it's just a standard notation for usual derivatives of functions of one variable. So what was new? So we discovered that actually the same thing allows us to construct invariants for nonlinear ODEs by just evaluating these expressions on linearizations along all solutions. So essentially what happens, our equation as a manifold is foliated by solutions. Then along each solution, we can consider its linearization. For this linearization, we can compute classical Wilczynski invariants. And then we can glue this classical Wilczynski invariants along all solutions, and we get something that is defined globally on the equation itself. And that's called generalized Wilczynski invariance. And technically, it's just simple substitution of derivatives of the right-hand side of our equation, so coefficients of the linearization into this formula. This way, we get expressions which are called generalized Wilczynski invariants, and I don't have, well, probably I have. For third order ODEs, one of the invariants W3 I mentioned at the very beginning of my talk is exactly this. Well, Wunschmann invariant is exactly the invariant of this kind. Then actually, if you know that, and Wilczynski invariants, generalized Wilczynski invariants are, of course, contact invariants, but automatically they become point and fiber preserving invariants because well, it's just an obvious observations that any contact invariant is point and fiber preserving invariant, and any point invariant is fiber preserving invariant, because we decrease the size of pseudogroups. So this is a result back to 2001 I mentioned. For contact ODEs, here is a complete description of, for contact geometry of ODEs, this is a complete description of fundamental invariants. So in a way, this is a complete characterization of trivializable ODEs. So first of all, if you have an ODE for the at least K4, we have Wilczynski invariants. There are K minus 2 of them. And again, indices here exactly correspond to the orders of these invariants, how many derivatives you have to take. Take into account that you count derivatives with weights. Then I introduce a very useful notation IR. So it's R times derivative of the right-hand side of the equation with respect to the yk plus minus first derivative of y. Yk minus 1 in jet notation. Then it turns out that I3, so 3 derivatives, is an invariant for 4th order ODEs. And starting from 5th order ODEs, it's just sufficient to take just 2 derivatives. And this I2 becomes already a relative invariant. And then we just need 1 or 2 extra invariants that form the system of fundamental invariants. For example, for k equal to 4, one needs to add, so for k equal to 4, we have W3, W4 as fundamental invariants, then we have I3, and then one more invariant, which is this, well, a bit strange form, but this is how it is. And then similarly for k equal to 5, we just need one more invariant on top of 3 Wilczynski invariants and I2. And for starting from dimensions, from ODEs order 6 and 7, that kind of starts to stabilize. So in particular, an arbitrary ODE is of order k is trivializable under contact transformations if and only if it has vanishing Wilczynski invariant, so all its linearizations are trivializable, which is a very natural condition. And in addition, there are a few more expressions that have to vanish. A question is, where do these invariants come? One finds out, as I mentioned, one finds out how many invariants there are and in which degree they sit via cohomology theory of Lie algebras. And then one just tries to compute Cartan connection very explicitly, and luckily for contact ODE, for the case of contact geometry of ODEs, one just needs to go to degree 4. It's not needed to compute all Cartan connection. It's just sufficient to compute explicitly a few first terms in the explicit expression for this Cartan connection. And here we get exactly these expressions. And again, this calculation is very not elementary, but it's just differentiation and solving linear equations, not linear ODEs even, but just linear algebraic equations. And it's perfectly done by Maple, for example, or any other symbolic computer algebra system. So one can push a button and see all coefficients of the Cartan connection for a given ODE and extract fundamental invariants from there. So part of this invariant, so for example, I did use computer algebra to compute this invariant, for example. And I don't have any easier way to do that. So it turns out that more or less the same computation does work for preserving or for point and fiber preserving transformations. And we get somewhat similar results, but with different expressions and lower degrees. So what we observe, for example, that's result for ODEs viewed under point transformations. First of all, we now treat ODEs starting from third order ODEs under point transformations. We still have Bolshinsky invariants as fundamental invariants. Then here we had I3 becoming fundamental invariant for contact geometry, starting from fourth order ODEs and I2 for ODEs of order 5 and higher. Here we have like a shift, a little bit like a shift. We have now third derivative like with respect to yk minus 1. It is now invariant for third order ODEs, and second starting from fourth order ODEs. Plus a few more invariants. Some of them are the same as in contact case, some of them are completely new. And again, I used computer algebra to compute these things. So this thing here, down here, is what we were not yet able to compute. So one more additional invariant is here, and the reason why it is very difficult to find explicit formula here is that unlike contact geometry, in point geometry, the degree of this invariant grows with k. So here we had like degrees were limited to 4 only. So here we have one more invariant that is of degree, I think, k, or k minus 1. And there it becomes really very difficult to, or even if not possible at all, to compute explicitly Cartan language for arbitrary k. That's too many terms and too many expressions to compute. So this is yet an open problem. What would be an explicit expression? We have conjectures here, but I'm not yet able to say more details here. And the same thing happens for fiber preserving transformations. So we also have Bolshinsky invariants here. Again, we have a shift of degrees, and we start from ODEs of order k of second order ODEs already. And here is a table of invariants. Again, some expressions. Some of them come from point geometry now and contact geometry. Some of them are new, like this one, for example. G4 for second order ODEs. And we still have an open question about additional invariants. In this case, there are, well, k equal to 6, that's only one additional invariant, but starting from order 7, there are 2 additional invariants. And again, their degrees grow with k. And that's not clear what would be the explicit expressions are. But there is a computer program, as I said, so a computer program would be able to compute Cartan connection and its curvature for an arbitrary given fixed ODE. So a condition for trivializability is the fact that the curvature vanishes. So if someone gives me an explicit expression of arbitrary order, I can put it into Maple and say whether curvature vanishes or not, and therefore I can say whether it's trivializable or not. But we'd like to have explicit formulae, which we were not able yet to find for these for their 7 and higher in case of fiber preserving endpoint transformations. Okay, so I think I'm done now. Any questions or comments?
Okay, Boris, thanks a lot. Yes, comments, questions. Well, quite impressive results. Okay, Boris, thanks a lot.
Thank you.
Thank you. Well, it was quite clear and transparent, but I believe that, well, you hid all the difficulties.
Yeah, well, I can say that the key difficulties, technical difficulties,
Yeah,
in computation of cohomology.
Yeah. And when computing cohomologies, Do you do it just straightforwardly, or some special techniques?
Special techniques like spectral
Special.
sequences.
Ah,
In this case,
well,
the
yeah,
spectral
yeah.
sequences are very short.
That's what I meant. Yes,
Yeah,
okay.
yeah, yeah, yeah. So there is a spectral sequence that works. One is called Serre-Hochschild spectral sequence that works for this type of problems. And luckily, that helps to identify. What is surprising here is that when you use the spectral sequence, we clearly immediately identify which part of the spectral sequence corresponds to Wilczynski invariance. So it's a very interesting match between purely algebraic computations and very geometric definition of invariance via linearization of differential equations.
Yeah, okay. Thanks a lot. So if the audience has no comments or questions, so thank you very much. Again, you are always welcome
Thank
here.
you.
Just tell me.
Mhm.
Well, goodbye. Thank you for being here. So we meet next time in the independent university. There will be a talk by Maxim Grigoriev. Okay. Thank you very much. Goodbye.
Yeah. Bye bye.